Hello everyone. So today we are here for our week 5 live session, that is Introduction to Proteomics. And today I'll be I'm so sorry. This is the main highlight of the session. So I'll be taking first the previous week doubt if you have any, and then we'll talk about the weekly summary, and then we have a practice question or the previous week assignments from the previous year course. So I'll be taking solution, and if you have any doubt, we'll talk about it. So this is our week 5, and in today's session, we have concept that is related to mass spectroscopy. So we'll talk about fundamental of mass spectroscopy, then I'll talk about a little bit of chromatography technology where you have a liquid chromatography which is associated with mass spectroscopy for better resolution of your result. Then you have mass spectroscopy, ionization source, and then mass spectroscopy and mass analyzer. So before I start with any of this particular concept, I would like you guys to please check all the previous coursework, and if you have any questions, any doubt, you can come and talk to me. You can write to me during this chat, and we can discuss this in detail. So quickly coming to mass spectroscopy based proteomics. So far we have talked about gel based proteomics where we have talked about 2D gel and the advancement of 2D gel as a form of DIG where we are studying the differential gene expression. And today we'll be talking about mass spectroscopy based proteomics. So it is basically not a gel based technique. It is using uh, instrument. It's a type of a chemical analysis. So if I talk about mass spectroscopy, it is one of the very powerful and quantitatively as well as qualitatively, and it's an analytical technique that is used to identify and quantify a wide range of clinically relevant analytes. So mass spectroscopy, it is an uh, analytical technique. So it is a type of chemical analysis that measure mass of ions and can calculate the relative abundance of each of these ion within the sample. So as I have already told you, so this is qualitative as well as quantitative. So qualitative, it give you quality of analytes, it give you all the details of analytes present in the sample. And when I talk about the quantitative, it also calculate the relative abundance of those ion within the sample. So I'm so sorry, I have a little cold today. But if at any point of time you cannot hear my voice, just let me know. So mass spectroscopy, as I have already mentioned when I was telling you that why we need to study chromatogram or chromatography, because when this analytical technique is coupled with the any of the chromatography, it allow the expansion of analytical capability to various clinical applications. So it give more detail, it resolve your chromatogram, and you get to know a lot about your analyte. Also, if I talk about the ability to identify and quantify protein, it is an essential analytical tool in the field of proteomics. So, if whenever we talk about proteomics or understanding a proteome, mass spectroscopy is one of the very important analytical tool. So, this is just an overview of how the machine look like. So, you have a sample source, then you have electronic beam that charge your analyte. Then you have positively charged repeller plate, then negatively charged accelerator and focusing plate. These are the part of some instrumentation, and I will not take every single point in detail because sir has talked a lot about it, but still I'll try to give you an overview. Then you have a neutral molecule, neutral fragment, and negative ion area which is like out from the vacuum pump. Then you have a magnet. Magnet actually align your ions in a different depending upon their charges in the different orientation. Then you have analyzer tube. Then you have a positively charged or deflecting according to mass to charge ratio. Then you have an ion slit, collector, and the recorder. So positive ions are detected, neutral species are undetected. So when you're giving a charge to something, you want it to be a single charge, which is a positive charge in this case. And if there is no charge on your analyte, it cannot be detected because based on the charge to mass ratio, they get resolved in the mass spectroscopy. This is again just a diagram of how spectroscopy imaging technique look like. It's general over workflow of your mass spectroscopy imaging technique. So you have a tissue sample, you make a tissue slide, then you code the sample with on a matrix plate, you take a data, you acquire the data, you analyze the raw data depending upon the mass to charge ratio and intensity in the graph, and then you process the data. So this is basically when things are associated with imaging. And then you have different type of ionization technique where you have MALDI, then secondary ion mass spectroscopy. MALDI is matrix assisted laser desorption ionization. It is one of the soft ionization. Then you have secondary ion mass spectroscopy SIMS. Then last one is DESI, that is desorption electrospray ionization. So mass to charge ratio, if any point of time, if I talk about M by Z, that means mass to charge ratio. And if I talk about FTICR, that is Fourier transform ion cyclotron resonance, and mass MS is mass spectroscopy. These are some terminology, or you can say some short forms that I might need, I might say during this particular lecture. So you should have a clear picture of what all these short form means. Now, this is the paper, these are the two paper, and I want every one of you to please go through these papers because they have talked about mass spectroscopy and protein analysis. So how you're going to use this technique to analyze the protein that are present in your proteome or in your sample is uh, these papers are very helpful for that. Just give me a minute. I'll take some sip of water. Yeah. So these are the paper. I want you guys to take a screenshot or just go through these papers because anyhow I'm going to share the link of this video so you can check these paper and you study these paper to understand the mass spectroscopy. It is very important analytical technique and it is important whenever we talk about proteomics. So without MS you cannot talk about proteomics these days at least. Now coming to the basic of mass spectroscopy. So if I divide the mass spectroscopy into three different aspects, first one is ionization. So you have a sample, you have to ionize the sample. So you are actually creating ions, then you are collecting or separating ions, and then you are analyzing or detecting them, right? So quickly, if I talk the three essential component of the mass spectroscopy, first one is an ionization source. What does it mean? It is where the molecule is given a positive electric charge either by removing an electron or by adding a proton. So there are two ways by which you can give positive charge to these uh, sample either by removing electron. If you remove the negative charge, it will get into a positive, it will acquire a positive charge. If there is a deficiency, it will acquire a positive charge, and or by adding a proton. So this is how you do the ionization. Then depending upon the ionization method used, the ionized molecule may or may not break apart into a population of the smaller fragment. So we have different type of ionization technique. It's a hard ionization and the soft ionization. Depending upon what kind of ionization method we are using, it may or may not break into smaller fragments. So we have to choose according to kind of analytes we're going to analyze. So sometime you're aware of this thing that these are protein samples, and sometime you know what analytes you are using. So depending upon that, you use the ionization method. So some of the sample molecule remain whole. So this will definitely happen that not all of your molecules get fragmented. There might be some molecules which are still intact. They are not divided into smaller pieces. Then there is a mass analyzer where the cation fragment are separated according to their mass to charge ratio. So see, if I'm talking about the mass to charge ratio, uh, as we have just studied that there are some molecules which will not get divided into smaller fragments. So the mass is higher, but they have charges. So but depending upon their mass to charge ratio, analyzer will arrange these sample. Finally, there is a detector, and this detector uh, quantify and separates your uh, ions. So basically detect and quantify the separated ions. So analyzer has already separated them depending upon their mass to charge ratio, and the detector is now going to detect them and quantify them. So this is just the basic. So first thing is ionization. So with the help of ionization source, you are providing them ions, you are making ions of these sample. Then you have analyzer which will separate your ions on the basis of mass to charge ratio, and then you have a detector which will measure and detect the separated ion, and you can easily analyze the data. Then uh, now if I talk about ions, so what are ions here? Why are we saying that? Why do we need to make ion, and what are these? So when electrically charged molecules that are ion, they are accelerated into ionic field. So this is the basic principle of mass spectroscopy. Now you have made the ions. You have ions. What will you do about these ions? So you will be taking these ions in the in the presence of electric field, and their speed will depend upon the ion charge to mass, charge to weight ratio, or charge to mass ratio. So if the molecule is bigger, it will take time to move. If the molecule is smaller, it will be faster. So by measuring the time it takes for the ion to pass a certain distance, the incidence of the different molecule in a test can be determined. So depending upon what timing these ions are changed, ions are taking, then you can easily tell that yes, uh, this particular ion is smaller in size, bigger in size, because the time they are taking will be different. It was impossible, however, to use this technique on a large molecule such as protein. So if you have a very large molecule like protein, before uh, s- uh, uh, before large ion could be produced in a gaseous form. So generally it is very difficult for you to do the time study of for the large particles of proteins. So then there was a time when large ions could be produced in a gaseous form. So in 1987, there is this scientist called Koichiro Tanaka. It showed that the laser pulse could blast apart the protein molecule so that ion in the gaseous form are produced. So when you are using a large molecule, you are using you are using it in a gaseous form. So it is in the form of gas. So and you are using laser. So with the help of laser, you are dividing these larger ions uh, into small fragments. So this is basically the time of flight, which is very important aspect of mass spectroscopy. So the principle of this spectroscopy is the measurement of time taken by an ion to travel down the flight tube to the detector. So time will depend upon the charge to mass ratio. Charges are there, but masses are different. So charge to mass ratio will differ. So the flight of a flight tube is straight uh, and like an any mass spectroscopy operated under the high vacuum to avoid interference from the air molecule. So the flight of these molecule in the flight tube is basically generally a straight flight, and you do this thing in vacuum so that there is no interference from the ion molecule. And if you could see here, so these are the this is the sample. You have done the ionization. Now there's a high voltage here, and here through the needle, the sample is passing, the ions are passing, and they take their flight on the basis of their mass to charge ratio. And all this thing happen in a vacuum so that there is no interference from the outside. Then talking about the ionization step. So as I have already mentioned, there is a hard ionization technique and then there is a soft ionization technique. What happen in hard ionization? Hard ionization, you require high energy that result in a greater number of fragments. So your number of fragment will be high. If you could see here, you have large number of fragment and the number of molecular ion is low. So molecular ion, basically the molecules that are making ion. So basically the intact molecule of a particular species is comparatively less. So that because there are a lot of fragments. So the integrity of the molecules disturbs. The number of molecule ion is low, but there is large number of fragment ion. Fragment ions are large and molecular ions are low in hard ionization. So other way around in soft ionization, there you require low energy. So low energy will make less fragment, but the high molecule ion. So if you could see, the fragments are not in in large number, but the molecule ions are very much intact. So you can easily read these. So here, if this is the molecule, this is break down into lot many fragments. So as a molecule, you'll not get a single peak, right? But in case of soft, you will get a single peak. Why? Because the fragments are less here because you're using low energy. So these are some desorption ionization methods. So if I talk about fast atom bombardment, which is called FAB, its impact of high velocity atom on a sample dissolved in liquid matrix. So this is how the ionization done. Then you have secondary ion MS, which is SIMS. SIMS is basically impact of high velocity ion on a thin film of a sample on a metal substrate or dissolved in a liquid matrix. So this is called liquid SIMS. Then you have plasma desorption. What happened in plasma desorption? So you have impact of nuclear fission fragment. Example from 252 CF on a sample. uh, just give me a second. Just 1 minute. Okay, so this is basically Californium 252. It is the source, and on a solid sample deposit on a from this, it is basically deposited on a metal foil. So this is through a nuclear fission method. Fragments are formed. Then you have matrix assisted laser desorption ionization, which is MALDI. It is impact of high energy photons on a sample embedded in a solid organic matrix. Then you have field desorption. So it is imposition of high electric field gradient on a sample deposition on a solid, special solid substrate. So then you have electron spray, which is a formation of charged liquid droplet from which ions are dissolvated or dissolved. So these are just different type of ionization methods. Then you have basis of mass spectroscopy. So if you could see here, then you have a mass of mass plus hydrogen one photon. Then you have two photons, so two plus charge. Then if you have three proton, then you have three plus charge. So the mass is same, but the charges are different. So the mass to charge ratio will be different for each molecule, and their time of flight will be different. So you will study these ions on a different time because they are different in charge, uh, despite having the mass same. So ion mass same or different हो सकता है depending upon what kind of molecule you are using, but charges can also be differ on same type of molecule. It may have one charge, it may have two charge, and likewise it may have three charge. Then MALDI that produces singly charged ion species result in large mass to charge species. So in case of MALDI, you have large mass to charge species. Just give me a second. I think there is a problem in my headphones. I need to put it back. Just a sec, please. Completely forgot. I think I'm audible. Okay, so coming to different type of ionization, one of the ionization that, as I've already talked about, that there is electron spray ionization. It is one of the more common type of MS technique used in organic laboratory. In this type of ionization, the ionization source, the sample, in this type of ionization method, the sample molecule is bombarded by a high electron beam, which has the effect of knocking a valence electron off of the molecule to form a radical cation. So if you could see here, high beam is getting these molecule, and now the electron is removed out, due to which it become positively charged, and that's how it has made its ions, because electron is removed out. Because a great deal of energy is transferred by this bombardment process, the radical cation quickly begin to break into smaller fragment, some of which are positively charged and some of which are neutral. So now when they it bombard, it create a charge void of electron. So this entity is very unstable, and it will further divide into smaller fragments, some of which are positively charged and some of which are neutral. So the neutral fragments are either absorbed into the wall of the chamber or are removed by the vacuum source. So neutral is not what we detect, so they are just removed by the vacuum source. So in a mass analyzer component, the positively charged fragment and any remaining unfragmented molecular ions are accelerated down a tube by a tube which has electric field. So depending in the electric field, these ions move and accelerated down, and the detector will detect these ions. So coming quickly again to the electron spray ionization, it has three stages. So one is droplet formation, dissolution, and then gas phase ion formation. So what is droplet formation? Droplet formation, under the action of a high voltage electric field, the sample solution is ejected from the capillary to form a charged droplet. So now the charged droplets are formed, because in the presence of high electric field, these sample solutions is ejected from the capillary to form a charged droplet. So now they are charged. Then you have dissolution. Dissolution, the droplets entering the spray of the chamber are evaporated by the counter current of the heat drying gas like nitrogen gas, and the diameter of the droplet becomes smaller, and the surface charge density increase. So the diameter is decreased now because of the evaporation, but the surface charge density increases. Why? Because the uh, droplet is reduced, the size is reduced, but the charge will increase, the density will increase because the size is reduced now. When reached to the Rayleigh limit, the Coulomb repulsive force between the charges is sufficient to counteract the surface tension of the droplet, and the droplet fission result in a smaller charge droplet. So basically these droplets then further divided into, and they become a smaller charge droplet. Then you have a gas phase ion formation. This is basically the size of the charged droplet reaches to a nanometer level, and the ions in the droplet turn into a gas phase. इतना smaller चला जाता है कि वो nanometer level पे आ जाता है. Now rather than a liquid, it will, you can call it as a gas phase ion. So they are very small in size. That's why they have become gas phase. They are into a gas phase. Then in electron spray ionization, you have different model. One is ion evaporation model. It is proposed by Erebrain and Thomson. IEM suggests that the ions are ejected directly from the source of charged droplet as the droplet shrink. So ions वहीं से directly spray out होता है, directly eject out होते हैं, because droplet धीरे धीरे shrink होता है in the presence of, where we have talked about that evaporation happen and droplet gets shrink. As the solvent evaporate, the surface tension competes with the increasing Coulombic repulsions until ion dissolve from the droplet into the gas phase. So this is what happened in IEM. IEM, it is one of the very is more applicable to the smaller and high charged ions where the field strength at the droplet surface is sufficient to expel ion. This model explains ionization process for a smaller molecule and peptide with relatively low molecular weight. So this is basically for the smaller fragments or the smaller peptides. So IEM emphasizes the critical role of local electric field on a droplet surface in enabling ion release without breaking the droplet apart. So this is what ion evaporation model is all about. Then you have charged residue model, which is CRM. It is initially introduced by Dole and later refined by Rolgin. CRM is basically CRM points that as a droplet continue to evaporate, the subsequential break into small droplets until one only a single analyte ion remains. वो इतना ज़्यादा टूटता जाता है. So you have a droplet, it is getting evaporated. Now ions इतने ज़्यादा टूटते जाएंगे जब तक लास्ट में एक सिंगल ना बचे, तब तक होता रहेगा ये. Then the charge is retained on the residue after all solvent evaporate, leaving a gas phase ion with a minimal fragmentation. So now because solvent evaporate हो रहा है, तो जो last में बचेगा that will be a gas phase ion and its fragmentation is minimum at that particular time. Then you have CRM is often considered more relevant for large biomolecules such as proteins. So IEM is for smaller molecules, CRM is for large biomolecules like proteins, where complete dissolution leaves behind a charged macromolecule. So you will have one macromolecule or a big charged macromolecule left after all the evaporation or dissolution happened. This model describes a gradual stepwise process where Coulombic fission result in droplets with decreasing radii, eventually leading to a charge and a light in the gas phase. So CRM is basically favored in context where analytes are larger and require more gradual solvent evaporation before ionization occur. So one method is for the larger molecules, another method is for the smaller molecule, and it has talked about the same uh, that eventually with the evaporation only one single analyte is left at the end. Okay, and in case of IEM, it is divided into smallest. It keep on you know dividing. uh, yeah, it eject out as many as charged droplet uh, during after the evaporation. Then these are just important term in ESI. So I have already mentioned that droplet formation is one of the very important aspect where the sample solution is ejected from the capillary under high voltage electric field forming a charged droplet. This is droplet formation. Then you have initial dissolution. As the droplet enter the spray chamber, heat dry gas like nitrogen evaporate the solvent. So this is dissolution, where after which you just left with charged molecules, leading to smaller droplet size and increased surface charge density. Size reduced, droplet size reduced, but the charge density increased. Then you have Rayleigh limit and Coulombic fission, where the droplet reduce and charge density reaches to a Rayleigh limit. इससे ज़्यादा one droplet cannot carry. That is the limit by Rayleigh. That is what is Rayleigh limit. Then the Coulomb repulsion counteract surface tension, causing the droplet to undergo fission into smaller and more highly charged droplet. Okay, then you have continued dissolution. The cycle of dissolution and fission continue as the droplet size decreases further, concentrating charges into a remaining droplet.
Then you have gas phase ion formation. As the droplet reach to a nanometer scale, the ions in highly charged droplets are eventually released into a gas phase, forming a gas phase ion ready for mass spectrometric analysis. So that was ESI. Now coming to MALDI, which is matrix assisted laser desorption ionization technique. It is a soft ionization technique used in mass spectroscopy that produces rapid and efficient ionization of a wide variety of molecules. MALDI uses a laser energy absorbing matrix to produce iron from molecule having molecular weight ranging from 100 to 1000 of the Dalton with a minimum fragmentation. So it has found increasing application over the last 30 years, especially for the analysis of biomolecule like protein, peptide, DNA, polysaccharide, and other large organic molecules like polymers, dendrimers, and other macromolecules. So these molecules tend to be fragile, undergoing excessive fragmentation when ionized by the more conventional method. So if you could see here, it is basically an allied matrix mixture where the where you target a laser beam, and then the matrix ion will form and they are moved to mass analyzer and the analysis happen. Then MALDI is similar in character of ESI, which is electron pair ionization, in that because both technique produce low molecular fragmentation on ionization. So they both belongs to a soft technique. A primary difference between MALDI and ESI is that the former typically produce ion with a net single charge. So generally in case of MALDI you have single net charge, but the mass is different. But in case of later one, and this enables simple determination of molecular mass from the most compounds. So you just have one charge, one net single charge, but the masses are different. So you can easily determine, it's a very simple determination of molecular mass from the most compound. However, it can also limit the ability of analysis that largest macromolecule protein. So definitely, if you have a larger molecule, a larger macromolecular protein detection is difficult when we talk about MALDI. So MALDI ionization is basically divided to three steps. First one is a sample is mixed with the soluble matrix material and applied to a metal plate. As the mixture dries, the crystals are formed on the sample material that are critical for efficient ionization. Then you have a pulse laser beam impinges into the sample, causing the desorption of the sample and matrix material. So now you have your ions. Now your matrix material will break down into a process to produce a gas phase ionic species. And then finally the analyte molecules are ionized by protonation and deprotonation in the hot plume of the ablated gases. The ions are then accelerated into the mass spectroscopy system and mass analysis. So this is all mass MALDI ionization methods. Then coming to mass analyzer. So you have different type of analyzer. So one is time of flight. As I've already told you that these ionic identity have different mass to charge ratio, so they have a different time of flight in the tube, and that is what we detect. So separate ions and it separate ions and measures, because analyzer is separate ion. Either they separate on the basis of mass, mostly separate on the basis of mass to charge ratio, and it measure their mass to charge based on the time they take to pass. So time uh, so it basically the time of flight is basically depend upon the mass to charge ratio. So if the mass to charge ratio is higher, the identity will take less time. Large more time. If the mass to charge ratio is less, the identity will take less time. So depending upon their mass to charge ratio, they take time to pass from the ion source to detector, and that is what time of flight analyze. And on the basis of this analysis, they identify the molecule or the ions. Then you have quadrupole. Here you have four rods which has these are the four rods, and where you have your non-resonance ion which is not detected because it does not have, it is neutral, it does not have a charge. Then you have a resonant ion which is get detected, and that's how you analyze. So the two opposite road with the positive potential, and there is a two opposite road with the negative potential. So you have positive potential, you have negative potential. They act as a filter, allowing only ion of a certain mass to charge ratio to pass of a certain filter. So basically you have a so these rods act as a filter, and depending upon their polarity, because they are positive and negatively charged, they only allow few ions to pass through it, and those ions will get detected. So the resonance here is on the basis of that. Then you have orbitrap where you have separation of ion in an oscillating electric field. Oscillating electric field is when you have one side has a positive a voltage, and then you have a negative voltage, so it's like oscillating, so it's like a AC current thing. So that is there in orbitrap. Then you have ion trap. In ion trap you have, that this is similar to quadrupoles. You trapping the ions and selectively on the basis of their mass to charge. So you are trapping it. So these ions are trapped depending upon their mass to charge ratio, and that's how depending upon their mass to charge ratio, the analyzer is separating them, trapping them, and leading to a detector. So detector will detect these ions. Then you have tandem mass to mass, ms by ms. Here you have uh, ms1 can help in identify molecular weight of the biomolecule, because this is basically double mass spectroscopy. So in case of first mass spectroscopy, where you are using different ionization and you are analyzing the data, so here you get the detail of molecular weight. Then again you pass this thing with other ionization method, so collision photon surface, where these different ions will further fragmented, and now in ms2 it is required for deducing the peptide sequence, because initially you have larger molecule, large biomolecule, so you are just getting the molecular weight of that, and then you are further fragmenting it, and that's how you get the sequence. So you get the peptide sequence, and then you combine this peptide sequence and detect what all proteins are present in your sample. So this is tandem mass to mass, mass by mass. So you have proteoforms. Then you are basically applying bottom up approach, where you are triptychally using trypsin, digesting the protein, and giving them the ionization and analyzing the peptide ions. And then you have a top down approach, where you have the complete protein, then intact precursor ion, and you are detecting these intact precursor ion once you have the molecular weight of these ions, you are further fragmenting it, and then you are detecting the fragment ions. So this is what happen in tandem mass by mass method. Then you have tandem mass by mass acquisition method. So this was just how the ionization done. Then how do you acquire it? So you have uh, just just give me a second. Yeah. So you have coming back to this, so do you have different acquisition method by mass to mass? This, the one is data dependent acquisition. It is a mode of data collection in tandem spectroscopy, where certain protein within a narrow mass range are fragmented. Only certain proteins are fragmented, and so first one will give you the survey scan and the precursor selection. So you will select few proteins. So for example, here there are only blue, red, green, yellow, and purple were selected, and only these protein will further fragmented, and then you study about these proteins. So they are further fragmented, and their peptide will be analyzed and sequenced, and now you get to know that what all precursors you have selected, details of all the precursors you have selected. Then you have DIA. DIAMS is DIAMS is data independent acquisition. So you are not selecting anything here, you are selecting it. So data dependent, you are actually selecting your precursors. In data independent, you are not selecting. The survey scan across all isolation window happen. So you are selecting everything here. Here no selection is dependent, so your data will not, you will not decide anything particularly from the data of ms1. You're completely fragmenting the everything, and all the window fragmentation of all the precursor in each window will be analyzed. So you are putting a window. This is basically dividing your sample into different you are dividing your sample. So when you have lot many when you do a proteome analysis, a large sample, so you divide your samples, you fragmentation of all precursors happens. You are just putting a window. So for example, in this particular area, what all proteins are present will come in this. In this particular window, what all proteins are present will come in second group. Likewise, this and this and this. So here you are taking everything, fragmentation of everything, but in a form of window. So you have set up a window where all the proteins present will be fragmented and analyzed in for that particular window. Then you move on to next window in case of data independent acquisition. In case of data dependent acquisition, you have selected your precursor. Once you have selected them, only details of that particular precursor will come in this. Okay, so here you have already decided what all precursors you want to study in your data dependent. That's why I said data dependent. It is depending upon your data from the ms1 first detection, which will tell you about the protein molecular weight. You are selecting them and then fragmenting. In data independent, you are just dividing them in a different window and then analyzing them in details. So this is mass by mass spectroscopy. Now coming to the mass parameter. So you have resolution, isotopic peak, and the charge state. So you have a different mass to charge difference between isotopic peak is 0.25, if you could see here. Then you have mass difference between isotopic peak is 1 amu, that is 1 neutron. So if you divide the 1 by point, this will give you 4. And if you have monoisotopic, like same kind of single peak with one single one peak, then you have the molecular weight multiplied by your charge minus 4. So this will give you the location of the peak. So this is how your peak get resolved on your graph. So this is what resolution and isotopic peak and charge state is about. So depending upon the different molecular weight and the different kind of a peak that you are getting, so sometimes your fragments are divided into more fragments, sometimes your ions are divided into more fragments, then it will become difficult. So for example, here it will become difficult to get to understand. So here you have the resolution is less as compared to this. You have single peak here. So here resolution is 60,000. Here resolution is 2,000. This is orbital trap. This is ion trap. Okay, so here you are getting all the ion getting trapped here, and that's how you're analyzing it. And here you have your orbit trap where you're using different strategy to analyze the peak. But the resolution is high here in case of orbit trap, not in case of this. Then mass resolution. So basically the width, the dimensionless ratio of mass to charge value of a peak divided by its width at the maximum intensity. So where you have the maximum intensity, that width is being taken and that will give you the resolution. So जितना ये पतला होगा, जितना तुम्हारी peak sharp होगी, that is more resolved because it is coming at a particular position. So that will be more resolved, right? Then coming to mass accuracy, I'm quickly taking all these concepts because then we have questions after this. But if you have any doubt, you can ask this thing in the next class. So mass accuracy here, mass accuracy is basically what you observe minus what theoretically the mass could be divided by. So basically it's like expected from observed minus expected divided by expected into 10 to the power 6. So that will give you the mass accuracy. So it actually tell you the how much accurate your data is. So exact mass is this, average mass जो experimentally आया है वो ये है, and that's how you come to mass accuracy. This actually help you understand your resolution, how better your sample is being resolved, that or how better your mass spectroscopy spectrometry experiment run is dependent on your mass accuracy. That's how your high resolution come. Then you have collision induced dissociation. Here you have a collision gas and or a collision cell. So your precursor ion are then collide into some ion, collision in a collision cell, where the collision will induce formation of more ions. So now product ions will be more. Okay, and that's how that you're going to detect in. So first detection, the ions were made, this is being detected. Now these ions are passing into another collision cells where other collision molecules are present, and when they bombard or when they collide with these molecules, they further produce more ions, and then you have your ms2. So these are some fragmentation pattern that people use. These are different type of fragmentations which will help you resolve your chromatogram. The more resolutions you have, the better is your mass spectroscopy analysis. Then you have electron transfer dissociation, where electrons are getting transferred and then they are further divided. So what happened, you have a peptide cations. They are either you transfer the electron, either you transfer the proton. So if you remove the electrons, then you have different excited charge reduced ion. If you are doing the proton transfer, you have different proton transfer product. So here you get proton transfer, and that's how you get the positive charge. Here you are removing the electron, and that's how you're getting the positive charge. You are creating void, you are adding something, and that will make a different type of ions, and that's what you detect. So this is basically electron transfer dissociation, because either you are removing the electron, or you are transferring the proton, and that's how you are getting the charges. Then understanding the ms chromatogram. So gradient in 120-minute chromatographic separation of the peptide for 120 minutes. So this is basically a different gradient which happened from 0 to 120 minute, and this is actually giving the separation of peptide. This is a good chromatogram, should be Gaussian in pattern with intensity in the range of E9. So basically, the more intense your peak is, better the chromatogram is. So illusion starting point and the end point is crucial. Why it's crucial? Because that will give you more intensified peaks, and that there is no hump or distorted peak to be detected initial में, because that is where your starting point is. So your ions will be start coming, so you will have a very sharp peak there. You will not get any hump, and that shows how good your chromatogram. So initially you should not have any hump, or at the end you should not have any hump. That shows that how beautifully your chromatogram has run. Okay, then here if you could see, the illusion started but failed in between. So यहाँ पर illusion start हुआ but still एक hump आने लग गया, यहाँ पे fail हो गया. So basically शुरू में ही you should have a single peaks. Okay, so issue either with the column or with the sample, that depends upon how purified your sample is. Because here you are, for example, if you take all the proteome of the cell, so you have a lot of protein, but then the lysis should happen in a way where you are not harming the identity of a particular protein. Also the column can be a problem. Why? Because if the column is not clean, or if there is an interference, you will definitely not have a good illusion of your ions. So this could be the problem, but hump should not be there. It should have a single and clear peaks. Then here chromatogram not so Gaussian in nature or dense, protein coverage won't be. So here you have single peaks, but chromatogram does not have a Gaussian in nature. That means it does not have a lot of, because what happened, your single identity, for example, something is coming at 5. So this particular position will have lot many peaks combined. Why? Because you will not have a one type of charge molecule of a single identity. So for example, what does that mean? So for example, if some molecular mass is 20, like there's a protein of 20 kilodalton, and it is divided into 10, 5 and 5, right? So the molecule that has 10, 5 and 5, it that will have, for example, first molecule has a 10 kilodalton of size. It will further divide it into either 8, either 10, either 8, either 7, either 5. So the here you will find different mass, same mass with different charge, and same charge with different mass of a single molecular identity. And that's how you have these peaks, these dense peak, and that is a Gaussian in nature. Here protein coverage won't be so great, so there is no uh, if you could see, there are only few peaks detail. Here you have more, right? So that's why the protein coverage here is not so much. This is basically understanding the gradient. So you have a flow rate, that is nanoliter per minute, which is, we say, nano LC, liquid chromatography. Then you have the solvent. You will use solvent, you can use different solvent depending upon the nature of your analyte. Here solvent A is water, solvent B is acetonitrile. Here it is given, see, acetonitrile, which is 95%. What kind of acetonitrile you have used, they have given the detail. It's a reverse phase chromatography, that means increasing hydrophobicity to elute out the hydrophobic peptide. So the more hydrophobic peptide will come late, the less hydrophobic peptide will come early. Then what is the D well volume? This is the system volume that from the point at which the mobile phase solvent are mixed until they reach the head of the column. So that is D well volume. Then you have it comprises the mixer, connecting tubing, and auto sampler loop as a primary component. So this is what the components are. So you have the solvent, you have the pump, you have the mixer, right, and the collecting tube. Then it is obtained, so then you have a D well time. अभी हमने बात किया volume का. Then we have a time. It is obtained by dividing the D well volume by flow rate. That will give you time. Then a system with the D volume of 3 ml run at a flow rate of 1.5 ml per minute would have D time 2.2 minute. Why? Because volume divided by the flow rate, and that will give you the time. Then you have delay created by the well volume can make a difference in a appearance of the chromatogram from the different gradient system. No effect on isocratic flow where component of a solvent mixture remain the same. So if you could see 1 minute 1 ms D time, 120 ms cycle time, that is 8.3 cycle hazard, that is 2.5 second peak width, and 21 peaks per week. This is 1 ms. This is 2.5. This is 5 ms. This is 10 ms. So all the details are given below. So here you will have 21 peaks. Here you will have 14 points per week. Here you have 21 points per week. So if you could see, there are 21 points. Here you have 14. Here you have 8 points. Here you have 4 points. Right? Depending upon different type time, different D-well time, you have different points on your peak. Then you have TOF mass spectroscopy. As I've already told you, it depends on the time taken by these ion to reach to a detector. That is time, that is distance upon velocity. We already have an equation for velocity, that is twice the kinetic energy upon my mass underscore square root of twice the kinetic energy, because it is kinetic energy is 1 by 2 1 by 2 m square v, right? So from there you will get the velocity. Now substitute this v in this, and then you get the time. So this is how you calculate the time. So that is given, and this is one example where 1 mole of a magnesium ion has a mass of this much. To find the mass of the ion, we need to divide it with the Avogadro number, that is 6.02 into 10 पर 23 से डिवाइड करना होगा उसके मास को. That's how you get to know the moles, and then you can put all these detail and you get the time of flight. Then again, this is the same thing, that you can have different questions. You can use this thing. I'm just moving ahead with this because then we have to solve question in detail. So here also you have a mass. Mass is basically relative isotope mass into 10 to the minus 3 upon may Avogadro number. And then you have kinetic energy, and I have given you that you can calculate the velocity from here, and velocity is basically distance upon my time. So here here they have given the question that this particular ion travel through top of a mass spectroscopy with the energy of 1.92 into 10 to the minus 6 15 joule. The ion take 1.09 into 10 power minus 5 second to reach to detector. Distance बता दिया उन्होंने, oh sorry, mass energy बता दिया, इतने जूल एनर्जी है, एंड देन यू हैव आयन का टाइम बता दिया. सो यू हैव टू कैलकुलेट द लेंथ ऑफ द flight tube. So uh, you have to calculate the distance. So you'll put all the calculate the velocity with the formula and then calculate the distance with the formula. So once you have the, because they have given the energy, they have given the time, uh, yeah, they have given the energy, they have given the time. So energy is given, calculate the velocity, and mass is also given. Then once you have the velocity, you can calculate the distance because time is also given. Calculate velocity and then calculate time. Then this is the now I'm starting with the previous year assignment week 5 for this particular week. First question is, what does the term reverse phase refer to in the reverse phase chromatography? Is it the direction of the flow of the molecule mobile phase, the stationary phase being less polar than the mobile phase, the use of reverse osmosis to separate analyte, or the detection of reverse elution peak? So if you can answer this question, you can turn on your mic or you can leave in the comment box. So what does reverse phase mean in reverse phase chromatography? It's a very simple question. Uh, can you just put it in the chat box? I think I cannot hear you. Can you hear me? Just leave the message in the chat box if you can hear me. I don't know if I can hear you guys. Can you hear me? Okay, I cannot see my the screen. So if you can hear me, just write in a message yes and try to give the answer of this particular question. Okay, answer is P. Yes, the stationary phase being less polar than mobile phase, and in the normal chromatography, the stationary phase is more polar, mobile phase is less. So here you have a reverse phase. So in reverse phase, everything is reversed. The stationary phase is less polar. Next question is, what is the primary purpose of the mobile phase in liquid chromatography? Mobile phase का primary purpose क्या है? Its purpose is to separate analyte based on their interaction with the stationary phase, to carry the analyte through the chromatographic column, to detect or quantify the analyte, or to provide stability to a chromatographic system. What is the answer for that? So you have to tell what is the use of mobile phase in a liquid chromatography. So what does it do? What does mobile phase do? So you have a stationary phase and then you have a mobile phase. So mobile phase interact with the analyte, or stationary phase interact with the analyte. Okay. No, it's not answer A. It's going to be answer. So mobile phase, to separate analyte based on the mobile phase is what interact with the stationary phase does not. Stationary phase is bound. So to carry the analyte through the, so stationary phase, on which mobile phase is basically what is doing, it is moving the analyte, so it is carrying the analyte through the chromatographic column. So stationary is fixed, mobile phase is what is moving. So mobile phase is helping the analyte to move in the chromatographic column. So answer here going to be B. Next question is, in a mass spectrum, a compound showing a prominent peak of mass to charge ratio at 45 and a smaller peak of mass to charge 44, what can be inferred from about the compound based on these peak? So is this a compound contain a chlorine atom? It is a compound containing bromine atom. Uh, okay. I think if you know the answer, that's well and good. Don't be sorry about anything. Okay. So, so you have two peaks, right? One is coming at 45 and another one is coming at 44. They are coming to almost I mean, this is basically a prominent peak which is coming at 45, and then there is a smaller peak which is coming at 44. So what can we infer? Does it contain chlorine? Does it contain bromine? Does it contain oxygen? Or does it contain carbon 13 isotope? So there is a difference of only single one. Uh, Okay, so answer here is the compound contains a carbon 13 isotope. So if there is a carbon 13 that is present in the sample, the mass to on and the okay, fine, I'll do this thing. I have to show you the calculation. Okay, wait a minute. I'll try to write it on this. Just give me a second. I'll try to write and show you. Wait. Okay, fine. In the next class, I'll show you with this because I don't think so it's working with me. I'll show you how this thing is divided. So how do you know that the peak is divided into smaller fragment and if it's coming just one? So here you have carbon 13 isotope that is actually increasing the mass by one, and that's how the smaller peak is coming in 40. I'll show you the division in the next class. Right now I'm coming quickly to the next question where you are analyzing. So the question 4 is, but the answer here going to be the compound contain a carbon atom of 13 isotope. Fine. Then coming to next question, that you are analyzing a mixture of, I think for these question I should have a detailed, explanation. So currently I'm traveling and I'm taking this class on my way to this place. So that's why I cannot unable to write as my device is moving. But in the next class, I'll try to give you more detailed answer. So next question is, you are analyzing a mixture of four on, and also I want to add this thing to you. So if you want to attend my coming classes, please look for the notification because there might be some changes in time, because right now I'm not in India and the time zone is varying. That's why I'm unable to take your class on exact time on Tuesday. So I'll be changing the timings or I'll be changing the day. So if you want to attend my class, please look for your notifications, because then you get to know that when is my live session is planned. Okay, so I just need this will be for next 2 weeks. So please, for the next two classes, look for the notification, because I might have to change the timing or might have to change the day of the class depending upon what NPTEL will suggest me. Anyways, coming back to the question number 4, you are analyzing a mixture of four compound using mass spectroscopy and obtain the following chromatogram. So this is what you are getting. The x-axis represent the retention time, and this is basically retention time. Wait a minute, I'll show you with the laser. This is the retention time and this is the intensity. Retention time is basically time it takes for a compound to elute from the column. So यहाँ पे आएगा उसने कम time लिया है, जो यहाँ पे आया उसने ज़्यादा time लिया है. As the time increases, that means they're coming late in, elute out late from the column. And y-axis represent the signal intensity. Identify the compound with the highest retention time. Can anyone tell me which compound shows the highest retention? It's very simple. So higher the retention time, that means highest time they are taking to come out. So which molecule have highest retention time? Let me just open my chat box. This is becoming very difficult these days. Okay. Answer. Has anyone given the answer? Please write it again because somehow, yeah. Okay, so the compound C, yes, compound C has the highest retention time because it's taking the maximum time to come up. Okay, next question is from the above question, identify which compound has the least abundance. Now you have to talk about the abundance in the mixture. So the uh, can anyone give me the answer, and then I'll tell you how you get to know the abundance. Which one has the least abundance? Which is present in a very low amount? No? Can you answer this? Or should I give you the answer? Okay, so abundance depend upon the intensity of the peak. If it is, yeah, okay, yes, molecule D. So if it is abundant, the intensity of the peak will be very high. If it is not abundant, the intensity will be low. So in high intensity show high quantity. Low intensity show low quantity. So the D component is least abundant. So next question is, you are tasked with analysis a complex mixture of a compound found in a water sample. The mixture contain both polar and non-polar compound. Which chromatography technique would be most suitable for the separation of analyte of this particular? So you have both polar and non-polar. You have to tell which particular chromatography you going to use. So when you have both polar and non-polar analyte, which chromatography you going to use? Anyone? B? Yes. So you're going to use liquid chromatography and you have both polar and non-polar. So in liquid chromatography you can use reverse phase or normal chromatography, both depending upon the kind of I mean you can decide depending upon the analytes you have. If you have the polar, I mean because you have both, so both can be used. So you can use reverse phase as well as you can use normal. Then you have this question, the following are the chromatogram of LCMS run on a two sample from a single study. Both samples were running under the same method file in the instrument from a deep global proteomic analysis. In your opinion, which of the two run will have better protein coverage? I have already talked about the protein coverage. Can you give me the answer now that which of the both are same? Both are run under LCMS. Both have the same sample, but they are run differently. Both samples were run using the same method file on the instrument for a deep global proteome analysis. So, which one has the more protein coverage? Okay, you are saying A. Yes. Why? Because you have it's giving more Gaussian type peaks, that means the coverage is high. Here you have distorted or where here you have a scattered peaks and less peak numbers, that's why this is not a better covered I mean this is not showing a better protein coverage. Next question is, which type of liquid chromatography is best suited for separating complex mixture based on charge? So based on charge, you have to tell which is type of liquid chromatography is best suited. Reverse phase, size exclusion, ion exchange or affinity chromatography. This is on the basis of charge base. So for charge based, you saying reverse? No. For the charge base, you have to use ion because there now you have different charges. So you'll be using ion exchange chromatography. I hope you gave the answer as A only, now, right? Then which I think this is fine. So if you have polar, non-polar, you will use reverse phase. If you have smaller and larger molecules, you will use size exclusion. If you have different ions, like different charges, then you use ion exchange. If you have affinity, for example, if some molecules are, are have a better affinity for a particular substrate, you will use affinity chromatography. Next, coming to the second last question of the class, which analyzer in mass spectroscopy measures the time it take from ion to travel a fixed distance based on their mass to charge ratio? So, which of the analyzer is based on the time? It's very easy. Is it a quadrupole analyzer, time of flight analyzer, ion trap analyzer, or orbitrap trap? Yes, it's a time of flight analyzer. In quadrupole, you have four rods. Two are positive, two are negative. So depending upon their charges, they only allow some of the mass to charge ratio molecule to oscillate between them. Then you have time of flight. Time of flight, the time your different ions take to reach to detector depends upon their mass to charge ratio and is what analyzed in time of flight. Then you have ion trap analyzer. You trap a particular ion identity and depending upon their property, they are eluted out. So that is ion trap. And then you have orbit trap where you are basically using oscillating electric field, and with that you have your different ion elute out at different time. So that is there. Then the last question for this class is, which ionization source in mass spectrometry involves the sample being vaporized and ionized by a heat filament resulting in formation of radical cation? So you're using a heat filament. So is it an electro spray ionization, atmospheric pressure photoionization, chemical ionization, or uh, electron ionization? So which one is this where you are using a filament? Okay, so sample is first being vaporized, sorry, and then you are using a heated filament for ionization. This is basically electron spray ionization. So I have given you all the thing where you are using evaporator, and once the evaporation happen, the density of charge get increases until it lead to Rayleigh limit, and then you have a Coulombic fission and your particle is divided into further ions. Okay, that's all from my side for today. As I've already mentioned, for the next two classes, please look for your notification. You will get a notification of when the class going to happen, as I am traveling and there is a time problem. So just stay connected with the mails and you will get to know when the next class going to happen. That's all from my side today. Thank you for joining. I actually cannot see who all are there. So I hope I see you next in the next classes. For the next two class, I again repeat that you have to check your uh, you saying something? Okay, can you just write it on the message because I cannot hear you. There's some problem because I'm traveling maybe. So I would say please check your notification for the course. And why I'm saying this is because I may have a different time for next two classes. Okay, anything you want to say, Shashikala? Can you just write it down because I think you're speaking but I cannot hear you. I don't know why. Can you type in the chat box, please, for me? Your voice is not audible to me. I can see that you are speaking, but okay, you want to submit assignment. So, you have a submission of assignment on the project on your course page only. You can submit it there, right? Can you hear me? Say yes or no. So when you have to submit your assignment, you can submit it there only. Okay, date is over, so I can't help you with that anyway. Like I cannot regulate the time of your assignment. Anyway, if the date is gone, still you try to submit it, they might consider it. Okay, so just go to the page and try to submit the answer, lock the answers. They might consider it, but they may not be. Okay, so try doing this because, okay, you are working. Even if you are working, please take out the time and submit. Try to submit on time for the next assignment. Try to submit it on time, because if not going to submit on time, I can't do anything about it. I'm just here to help you guys to answer those questions. Okay, fine, thank you so much. Okay, that's all from my side. Again, join the session whenever the date, you will get a mail of date when you have a live session with me. It might not happen on the same time because, as I've mentioned, there's a time difference. I'm traveling right now. So, in case, yeah, in case, thank you, Shashikala. In case you find, just check your emails, okay? You will find the details of next coming session. Okay, fine. Thank you so much for joining. See you next week.